Okay, VSEPR. Even though this is spelled VSEPR, it's pronounced VSEPR. And now we're going to move from two-dimensional Lewis structures into 3 dimensions. Okay, molecules are actually 3-dimensional structures. They don't actually look like two-dimensional Lewis structures. Lewis structures are helpful, but they're not 100% accurate. And so we try to look at them in 3 dimensions to get a little bit better understanding of them. That's where VSEPR comes from. So VSEPR stands for Valence Shell Electron Pair Repulsion. So what this means is that the shapes are determined by the electron pairs, hence the electron pair, and it tells you that they're going to repel each other, aka they don't like each other. So valence electron pairs are your bonds and your lone pairs. And they want to get as far away from each other as possible. And that is pretty much the crux of this entire thing. So we can look at it several different ways. So if we look at 4 bonds, this forms what we call a tetrahedron. Think of like jacks or something like that. Or if you could, a tripod with a pole coming out the top. When I do this for my students, I give them candy and toothpicks. And so they literally stick the toothpicks in, make a tripod, and then make another one come out the top. And it forms a 3-dimensional shape called a tetrahedron. Okay, there are no lone pairs in this shape, so it doesn't do anything strange that way. And so it always forms a tetrahedron. All right, next one. If I have 3 bonds, if I have 3 bonds with no lone pairs, then I get what's called trigonal planar as my shape. And what's going on there, it's kind of, as the name implies, they're all flat in a plane. So this is perfectly flat in a plane, and it is what we call trigonal, meaning it has forms 3. So if you take your, whatever you're sticking toothpicks in, you lay it flat on the table, stick one in at the top, and make a Y essentially, and you get this shape. Okay, and so because without there being anything else here, this is as far away as they can get away from each other. They're 120 degrees. That is as far away as they can get from each other. All right. Now, if I have 3 bonds and a lone pair, things change. Because that lone pair is going to come in and it's going to, instead of being flat like this, the lone pair is going to push them down into a tripod-like arrangement. And when they're in a tripod-like arrangement, we call that pyramidal. Okay? So that's what we're going to see that lone pairs do. Lone pairs push the bonds away from them. So when I have 3 with no lone pairs, it's nice and flat. But as soon as I add that lone pair, it's going to push them down and away from the lone pair, creating this pyramid shape. We're going to see that again when we look at 2. If we don't have any lone pairs, there's no extra lone pairs here, we get something that's nice and straight. We call this linear. Okay? Carbon dioxide is a good example. Okay, this is a linear molecule. It forms a straight line, just like this. What do you think is going to happen if I add a lone pair in the center? Just like with 3, when the lone pair pushes the other ones down and away, that's what happens here. The lone pair pushes this down and out of linear. It looks kind of like a sad face, but that's not really what's going on. So this lone pair pushes these bonds down and away from it, causing it to form what we call a bent structure, which is usually written like this. So back in the last lesson when we were looking at water, this is what happens with water. It's H2O. It's got an H, an O, and an H. But it had 2 lone pairs here in the center. And they don't cancel each other out. They bend it down and make it into a bent shape like this. So water has what we call a bent shape. And then finally we have, if we only have 1 bond, it's always linear. There is no exception there. Okay? So just running through these again real quick. I'm going to go back and get to the beginning. So if you have 4 bonds, you have what we call a tetrahedron. Tetra meaning 4. Okay, hedron meaning, if I remember correctly, faces. So this shape has 4 faces on it. But it's a tripod or a pyramid with another bond coming out the top. If I have three things by themselves, we call that trigonal planar. If it has a lone pair, then it's going to force those three from being flat and plane. It's going to force them into a pyramid shape. Okay? That's what the lone pair does. It forces them down into a pyramid shape. Same thing with two bonds. If there's no lone pairs, it's nice and straight and it's nice and linear, all in the same plane. But as soon as I add that lone pair, it bends them down and away, going from linear to forming something called bent. And then finally, if I only have one bond, the only way to connect two things is linear. Doesn't matter how many lone pairs you have, there's just no other way to do it. Okay? Alright, so they're based on the Lewis structure, so you have to do the Lewis structure first. And then, like I said, so the presence of lone pairs is key. They will bend one shape into another. If it's trigonal planar and you add lone pairs, you get pyramidal. If it's linear and you add a lone pair, you get bent. And to me, that is the simplest and easiest way to think about VSEPR shapes. Your books that you have to teach out of may have other shapes, but I really limit it to these just because these are the main ones and the simplest ones, and all that high schoolers in a regular chemistry class need to be exposed to. They don't need any of the weird ones or anything like that. Just keep it simple. Tetrahedron, trigonal planar, pyramidal, linear, and bent. Those are your 5 primary shapes. The weird ones just don't come into play in a lot of advanced chemistry, unless you get into really more like weird material science stuff. All right, so that's VSEPR, and that is the end of the covalent unit. So congratulations, you made it through your first nomenclature unit, and we will move into ionic in the next unit.